So to start, what we're looking at is an acid, and we know we're looking at an acid for a couple things. So first off, they tell you that in the question, so we can focus on that being an acid. The other thing that we could do to try and hopefully remember is that functional group written there or drawn there is a carboxylic acid. So it's called an acid. So that should help us realize that it's an acid. Once we know that it's an acid, we have to also remember the definition. It is a proton donor. So if it is a proton donor, it has to lose a hydrogen. So now the question is, what hydrogen within that structure is the acidic one? Well, if we'd remembered our carboxylic acid functional group, we'll hopefully realize that the acidic hydrogen is that guy. So if it's a proton donor, that hydrogen needs to come off the structure. So I'm going to leave a big space here, which will hopefully actually be big. And I'm going to draw the resulting structure. Where that hydrogen has now left the structure. So I'm no longer going to show the sigma bond connecting it there. The other piece that might be helpful for us when trying to do anything about predicting reactions or stability of reactions is to include the lone pair electrons. So each of those oxygens started with 2 lone pairs. We did nothing to those lone pairs, so they're going to stay connected to our oxygens. And now what we need to wonder about is what happened to the sigma bond that connected the oxygen and hydrogen. Well, oxygen is more electronegative than hydrogen, so those electrons should be pulled towards the oxygen. Okay? Another tip-off is that as an acid, it is a proton donor. If the electrons went with the hydrogen, it wouldn't be a proton anymore. It would be a proton and 2 electrons. So since we know it's a proton donor, that must have come off as H+, which then means the lone pair electrons must be on the oxygen. If we now go through our formal charge rules that we did way back when in Unit 1, or had it memorized, we would know that that oxygen would be negatively charged. Okay, and so what we've now drawn, is what is known as the conjugate base. Okay, conjugate because it looks most similar to our acid. Whoops. But it's a base now because if I tried to reverse the reaction to get the original acid back, I would have to put a hydrogen back or onto this conjugate partner, which means it would have to act as a base. Okay? The next part, we have to address the bases used to deprotonate this. Okay, so that means we have to run a reaction. Oof, this is getting crowded, so I'm going to have to remove some information. I have to react it with a base. So the question becomes, what base do I use? Before we start drawing in that base, let's consider what would happen to it. Well, it would have to accept a hydrogen. And actually, I'm going to pick a different color to represent our base. I usually pick blue, but it's early in the morning and I mispicked colors. That base would have to be a proton acceptor. It's not just accepting it from nothing, it's accepting it from the acid, which means that H+ needs to be connected to whatever our base is. I just dropped my pen. Okay, so, whoops. Whatever the base is, so that's my generic term for base. Our generic term for the base has to somehow connect to the hydrogen. You'll note that the electrons or the bond that I'm showing there, that sigma bond, I'm showing in purple. Because what I'm trying to represent is that the base had to donate those electrons to supply that. Why did the base have to do that? Well, remember when we split the hydrogen from the structure, it was split as H+, okay, which meant that it doesn't have electrons. Okay, so that sigma bond is coming from the base. This is now known as the conjugate, okay, and conjugate, because it's now tied to our base. Okay, so it's the conjugate partner of our base, because it's most similar to it. The base is the core functional group in both. But conjugate acid. Why is it an acid? Again, if we reverse the reaction and go backwards, it has to donate that hydrogen, which means it's going to act as an acid. Okay, so there's the basic kind of, simple labeling that I think would be helpful to have within this. The next part, and here's where I'm going to go through and now start erasing some of that text, is I need to go through and put in some examples for bases. So let's go through and start with the sodium hydroxide. Actually, we're going to hold off on that. We said that our base was a proton acceptor. And a base being a proton acceptor isn't a bad definition, but it's hard to tell if you have a proton acceptor unless it's accepted a proton. Okay? So when I'm looking at the list of bases, how do I know it's accepted a proton until I've forced a proton onto it? So one of the other things that we could use is call them electron donors, okay, which is the same thing as our Lewis base definition, but we're looking at the raw application of it, and it can be better to sometimes refer to it as an electron donor. So if we start with to be an electron donor, it would need to have electrons. Okay? If it had a bunch of electrons, it might even have a negative charge. So those are things to be looking for on our structure to decide if it is a base. So we could start with the sodium hydroxide. Okay, well, sodium hydroxide, one of the tip-offs that we're looking at here that we have a base, and this is what was in Chapter 7's homework on deciding if you have an electron-rich or an electron-poor atom. Bases, by definition, are going to be electron-rich. That sodium is a spectator ion, and that sigma bond that was between the sodium and the oxygen is really shown as a pair of lone pair electrons on the oxygen with a negative charge. Okay, so this should be a big red flag that this is probably going to be a base that is successful in our reaction. So what we could go through and do is run the reaction. It needs to pick up that hydrogen. The product of this would be H. There's our bond. OH, also known as H2O. Okay. Other things we could do with this is sodium hydroxide is a strong base, so it probably would work. Okay, so how could we go through and evaluate this? Well, there's two approaches. Okay. Sometimes you have to go the pKa route, sometimes you don't. So the non-pKa route is applying those rules: charge, size, electronegativity, resonance, and induction. Officially, we got another one. Okay, so those primary characteristics can help us evaluate this. But if we're going to do that, it typically makes sense to look at the base, because what we're talking about is the electrons, and the electrons are most obvious on the base. So if I go through and take a look at my hydroxide, okay, the base on the reactant side, okay, that is charged, right? If I look at the base on the product side, well, that is also charged. Okay, so charge isn't a useful rule to use. We could then move to the atom size. We're talking about an oxygen, still oxygen. Electronegativity, which is still oxygen. So it's the same in both cases. And then we can move to resonance as a question. So is there resonance in the hydroxide? No. Is there resonance in the carboxylate? Well, yeah. There's resonance because that negative charge can be dispersed through the pi system of the carboxylate salt. Okay, so there is resonance. I don't know why I wrote an O next to that resonance. That resonance stabilizes that species. Okay, so if it becomes more stable, which is more likely to form, the left side or the right side? The right side is more stable. Our reactions will always transition to things that are more stable. It's one of the things that's kind of nice about them, or favor the side that's more stable. So we would now say that yes, sodium hydroxide does indeed deprotonate the carboxylic acid because it produces a more stable species. Okay? I said there was another way we could do it. We could look at pKa's. If we're going to go to pKa's, what we need to do is have the pKa's of some particular functional groups memorized. So this is where I told you should memorize the pKa of a carboxylic acid, and it comes in about 4. You should also memorize the pKa's of some other common functional groups, like an OH, okay, for an alcohol. And while this is not technically an alcohol, it's pretty dang close as water. And that pKa is 15.7. Okay. I did just do a bit of a leap there, so I'm going to pause for a second. Okay. When evaluating the pKa's, we have to be looking at the acid species, in both the acid on the reactant and the conjugate acid on the product, and we're making a comparison between the pKa's between those. So if we're going to use pKa's as our argument for how we go through and evaluate, we want to pick the largest pKa is the weakest acid, okay? Which would then mean it's also the most stable. So if we go through and evaluate, the carboxylic acid on the left has a 4 pKa. Our conjugate acid on the right, water, has a 15.7. That would favor the products. Okay. Well, if we look at it, how did we get the products? We deprotonated the carboxylic acid, which means sodium hydroxide is a valid answer. Okay. So let's go through and do that again for one more of them. Okay, again, what I want you to be thinking about is addressing all of these pieces. So there's 2 processes behind this. Writing out all our reaction. If we set it up in this kind of basic system or this core system, we don't have to rewrite the carboxylic acid reaction. We just have to rewrite our base reaction. So we're going to move to a different base. I'm going to move to, and I'm going to go ahead and color code it so it stands out a little differently. I'm going to move to H2O. So I'm going to start with H2O. If H2O is now going to act as a base, it must, damn it, blue is a horrible color for this. Never mind, I'm not color coding it, I'm keeping it purple. So if it's going to act as a base, it must accept that hydrogen from our carboxylic acid. And what we would get as an answer is H2O, okay? Also known as H3O+. Okay? So, based off the same rule sets that we could go through and do as we did before, we could evaluate based off of charge, size, electronegativity, and all of that. That's comparing water to our charged oxygen-oxygen resonance, yes, stability thing, our conjugate acid. Well, water is not charged. Because water is not charged, we have our difference right out of the gate. Water is going to be more stable than our carboxylate. What does that mean? Well, if water is more stable, no reaction occurs. Okay? There's no reason to do that transition because the more stable thing was on the reactant side of the equation. Okay? So we're getting a different answer, which is cool. This is what's helping us to decide how this thing works out. We could also go through and evaluate our pKa's. We're going to evaluate again the pKa of our acids. So that's going to be the carboxylic acid, and that's going to be our conjugate base. Okay? The conjugate base is H3O+. If we had pKa's memorized, it's negative 1.5. Okay? The largest pKa is the weakest acid and therefore the most stable. We're comparing negative 1.5 to 4. 4 ends up being our more stable. The carboxylic acid doesn't deprotonate in the presence of water, okay, or doesn't deprotonate a lot. Okay? And as I was kind of alluding to in the email that I sent kind of back and forth with you, is that some of these reactions you're going to have to do the pKa argument on. Okay, so you're going to have to write those out and evaluate them. You should go through and make the pKa argument for all of them, each of those reagents, and make the base strength based off of comparing charge size, electronegativity, resonance, and induction as well, so that you can get an idea for that. When looking for pKa's, you can just look up tables of them on the internet. You do have to be a little bit careful with the amine, the NH3 here, or you can look up pKa's based off the ones that I told you to memorize. The only one that would, again, be tricky would be that NH3. Okay? So hopefully that will give you a little bit more guidance on solving that. Because it's anonymous, I am going to post this so everybody has access to it as well.